Tantor Audio, a division of Recorded Books, presents The Story of Evolution in 25 Discoveries, The Evidence and the People Who Found It, by Donald R. Prothero. Narrated by Tom Parks. Publisher's note: the print and e-book versions of this book include visual content, such as figures, tables, and photographs. There is grandeur in this view of life, with its several powers, having been originally breathed into a few forms or into one, and that, whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning, endless forms most beautiful and most wonderful have been and are being evolved. Charles Darwin, 1859. Nothing in biology makes sense except in the light of evolution. Theodosius Dobzhansky, 1973. Preface. Since the publication of my book, Evolution: What the Fossils Say and Why It Matters, Columbia University Press 2007, 2nd edition 2017, the fields of evolutionary biology and paleontology have made many new discoveries. Meanwhile, the evidence for evolution has been piling up and accumulating since publication in 1859 of the revolutionary book On the Origin of Species by Charles Darwin. Some of that evidence is discussed in my first evolution book, but much of it is new or mentioned only briefly in that book. Rather than focusing exclusively on the fossil record and spending a lot of time correcting the lies and myths of the evolution deniers, I thought it would be interesting and useful to focus on individual lines of evidence that led to the discovery of evolution, and the powerful insights they give us into the way that life works. Mara Grunbaum's WTF Evolution, A Theory of Unintelligible Design, 2014, and other books have made the point that life is full of bizarre and funny and ugly things that make no sense in a divinely designed universe, showing how clumsy and wasteful nature can be. However, that is basically a picture book full of jokes and one-liners, with a hip, irreverent attitude. I want to make the same point in a more serious way, exploring this topic and delving deeper into its meaning. In addition, I enjoy writing in the format of the 3 previous books in this series: The Story of Life in 25 Fossils, Columbia University Press 2015, The Story of the Earth in 25 Rocks, Columbia University Press 2018, and The Story of Dinosaurs in 25 Discoveries, Columbia University Press 2019. Each chapter in this book, as in the previous titles, is a self-contained vignette describing one particular idea, often wrapped in the historical context of how people have thought about this topic. As in the previous books, the science is often framed in terms of the stories of the people who made the discoveries and the importance of the discovery in the context of science. The book is organized into 5 sections. Part 1, In the Beginning, Everything Evolves and Earth is Very Old, describes how evolution is happening throughout the universe, which is billions of years old. Chapters 1 through 2. Part 2 discusses Darwin's original main lines of evidence for evolution and the related discoveries that have happened since Darwin's time. Chapters 3 through 9. Part 3, Great Transitions in the History of Life, talks about the dramatic evidence from the fossil record illustrating how certain major groups of organisms evolved from something completely different, or macroevolution. Chapters 10 through 16. Part 4, Eyes and Genes, describes the enormous volume of evidence from genetics and molecular biology. Chapters 17 through 19. And it also deals with the famous conundrum of how a complex structure like the eye could evolve. Chapter 20. Part 5, Humans and Evolution, details the evidence supporting the idea that humans are apes and evolved much like any other organism. Chapters 21 through 24, and where future evolution might go and will not go. Chapter 25. Like Darwin did in 1859, I hope to convince you, the reader, of the reality of evolution by building the case one anomalous fact of nature at a time. Each is clear evidence of evolution, and I hope you will be persuaded of the wonders of evolution just by the sheer, overwhelming weight of the evidence. This contrasts with my first evolution book, which was more scholarly and philosophical, and dealt directly with creationism and the broader topics around evolution. So sit down and prepare to explore the wondrous and bizarre aspects of nature that show how it has a history and how it evolved and changed through time. As the great Theodosius Dobzhansky wrote in a 1973 essay, repeating these words in his title, "Nothing in biology makes sense except in the light of evolution." Part 1. In the beginning. Everything evolves, and Earth is very old. Chapter 1. Discovery of the evolving universe. Everything evolves and changes. There's nothing constant in the universe. All ebb and flow, and every shape that's born bears in its womb the seeds of change. Ovid, Metamorphoses 15, 8 CE. Pantokraeo kai udent mene. Everything changes, and nothing stands still. Heraclitus, circa 500 BCE, as quoted by Plato in Cratylus. Our view of the universe and the solar system has changed dramatically in the past 500 years. Before 1543, almost all humans thought the Earth was flat and was at the center of the universe, and that the stars were tiny points of light on the dome of the heavens, figure 1.1. In 1543, Copernicus provided evidence for the idea that the Sun, not Earth, was at the center of our world, and that Earth was a planet in orbit around the Sun. In 1609, Galileo used a newly invented device called a telescope to discover that the stars were beyond counting, and that they were not scattered on a big dome over our heads. He also confirmed that Jupiter has its own moons that could move completely around it, showing that it was not sitting in a perfect celestial sphere or dome above Earth. He debunked the notion that the planetary bodies were perfect and unsullied when his telescope revealed that Earth's moon is covered in craters and is not a perfect celestial sphere. Finally, by discovering that Venus has phases similar to those of Earth's moon, quarter Venus, half Venus, etc., he showed that Venus was moving around the Sun in an orbit inside our own orbit. Most important, he confirmed Copernicus's idea that Earth was just another planet orbiting the Sun. By the 1670s and 1680s, Isaac Newton had worked out the laws of motion and gravitation, illustrating how the entire system could be explained by basic physics. Today, we look at the amazing images of space coming from both land-based telescopes and the Hubble Space Telescope, and we see what no one could have possibly imagined even 30 years ago. We can see the stages of how stars are born and die, and how other planets and solar systems have formed. These images, and the astrophysical calculations and models that explain them, give us a new view of the origin of the solar system and allow us to explain much of what was simply guesswork before this century. Where did we come from? When and where did it all begin? These questions have fascinated and troubled people since humans first looked at the skies. For millennia, the explanations came from a wide variety of religious myths and stories representing every culture on Earth. Early in the 20th century, it became possible to go beyond myth and speculation, and we began to use the methods of science to discover what really happened. The first breakthrough came from a number of women astronomers, figure 1.2, working at Harvard College Observatory under W.C. Pickering. They were known as the Harvard Computers because they were talented mathematicians who could quickly make calculations and computations in their head and on paper and do measurements by hand. Only much later did the word computer come to mean the electronic devices we all use. Pickering hired them because they were not only good at math, but also careful and meticulous in studying and analyzing thousands of glass photographic plates of the night sky, shot by different telescopes. They were also cheaper than male assistants, 25 cents an hour, less than a secretary, and worked hard without complaining 6 days a week. This was a time when most women were barred from scientific careers completely, and those who tried to get an advanced education in science met huge barriers every step of the way. However, their talents soon emerged, and they each made discoveries that revolutionized astronomy and outshone most other male astronomers of their time. The most famous was Annie Jump Cannon, who cataloged the stars of the night sky and proposed the first system of star classification, which was based on their temperatures. She built upon the first complete star classification system by Antonia Mori. For our story, however, the key woman was Henrietta Swan Leavitt. She was assigned to study variable stars, classes of stars whose brightness fluctuated from one night to the next. She soon realized that their brightness variations had a regular period of fluctuation, with the brightest stars, most luminous stars, having the longest periods of brightness variation. She found variable stars in a cluster in the constellation Cepheus, thus known as Cepheids, that were all the same distance away, which allowed her to calibrate the brightness spectrum. In 1913, after studying 1,777 variable stars, Leavitt worked out the relationship between the period of brightness fluctuation and the luminosity of these stars, which enabled her to determine how far away from us a star was by measuring its luminosity and its period of fluctuation. Thanks to Leavitt, astronomers now had a reliable tool to measure how far away a star or galaxy was from Earth. The next step was made by the legendary astronomer Edwin Hubble. In 1919, he was assigned to work at the newly completed Mount Wilson Observatory, Figure 1.3a, in the mountains above Pasadena, California, and he had free use of what was then the world's most powerful telescope, a reflecting telescope with a 100-inch mirror, Figure 1.3b, Figure 1.3c. His first major discovery in 1924 used Leavitt's Cepheid variable stars to show that what astronomers had known as spiral nebulae were in fact galaxies outside our own Milky Way galaxy, and that the Milky Way was just one of many galaxies. This expanded our understanding of the size of the universe far beyond what people had once thought possible. Hubble used the telescope to systematically study as many stars and galaxies and other large celestial objects as he could. He measured their distance using the Cepheid variable method, and he also used the work of Dutch astronomer Vesto Slipher at Lowell Observatory in Flagstaff, Arizona, who analyzed spectra of light from stars. Just as a prism splits sunlight into its major colors, the light from stars also can be split into a spectrum of colors, Figure 1.4. This spectrum, however, has distinctive bands across the color scale that are caused by the absorption of certain elements. When we analyze the spectrum of burning sodium or other metals in the lab, we find these same bands, and we can identify the elements we are seeing in each set of bands. Hubble's major collaborator in this effort was Milton Humason, who had no education beyond age 14 but was eager to prove himself. Humason originally drove the mules that hauled the telescope and other materials up that steep mountain. He then became a janitor during the night shift when the astronomers were at work, so Hubble got to know him. He found that Humason had unexpected talents and promoted him to be his assistant. Hubble admired Humason's quiet determination to take the difficult photographs and to do the careful measurements of the spectrum of thousands of photographic plates from the telescope. After measuring hundreds of different stars and galaxies, Hubble and Humason noticed something peculiar. The nearest stars had absorption lines in their spectra that resembled the same spectrum for that element on Earth. But the farther away the star or galaxy was from Earth, the more the white absorption bands were shifted from their original position and toward the red end of each spectrum. Why did the absorption lines move toward the red end of the spectrum? This discovery had first been reported and explained for a few galaxies in 1912 by Vesto Slipher. It is known as a Doppler shift and is caused by the Doppler effect. You have experienced the Doppler effect for sound many times. For example, if you are standing on the street when a car or train rushes towards you blaring its horn, you will notice that the pitch of the sound gets slightly higher as it approaches. Once the vehicle has passed you and is rushing away from you, you will hear the sound of the horn drop in pitch again. The Doppler effect is caused by the fact that the sound waves become bunched up as their source approaches closer and closer to you. If the waves are bunched up and have a shorter wavelength, they have a higher pitch. Similarly, when the sound source travels away from you, the waves are stretched out. Figure 1.5. Longer, more stretched out waves have a lower pitch. The Doppler shift applies to light waves as well as to sound waves. If the source is moving very rapidly toward us, the light waves will be bunched up and have a shorter wavelength, which corresponds to the blue and violet end of the light spectrum. However, if the light source is rapidly moving away from us, the light waves will be stretched out longer, which corresponds to the red end of the spectrum. Slipher's first observations in 1912, and then Hubble and Humason's careful catalog of more than 46 galaxies and many stars, showed that almost all of the observed galaxies were red-shifted. There were almost no blue-shifted objects that might be moving toward us. More important, Hubble and Humason found that the objects farthest from us had the greatest red shifts and must be moving away from us the fastest. Hubble and Humason's work suggested that the universe was expanding. It's analogous to making a loaf of raisin bread. When you start with the ball of dough, the raisins are all packed close together. But as the ball of dough expands, each raisin moves apart from every other raisin, and those raisins on the outer part of the ball of dough move the fastest. The universe is expanding. This is a staggering thought, and at first most astronomers were not able to accept it. However, Hubble and Humason's data were solid, and as time went on and more objects were analyzed, they all turned out to be red-shifted. In 1927, Belgian astronomer and Catholic priest Georges Lemaitre postulated a model in which the universe had expanded from a single point in the far distant past. Most astronomers did not like the idea that the universe had a beginning. They thought it was in a steady state of expansion, with new matter created at the center all the time. One of these steady-state advocates, Fred Hoyle, coined the term Big Bang to mock Lemaitre's model, and that name has stuck ever since. The controversy of Big Bang versus steady state continued for about 30 years until the late 1950s without any clear consensus. Then a crucial discovery was made. Not by astronomers, but purely by accident by two physicists and engineers, Arno Penzias and Robert W. Wilson, figure 1.6. In 1964, Penzias and Wilson were employed by Bell Labs, the original research division of AT&T Bell Telephone, which was responsible for improving the technology of communication for Ma Bell. They were working on improving the first antennas for receiving and transmitting signals by microwave, primarily to enable communication with NASA's Project Echo, the first attempt to use satellites for global communication, and later with the Telstar satellite. As the chief scientists and engineers on the project, their main job was to get the bugs out of the device and improve its efficiency. They found and eliminated many sources of noise from the antenna, but then they found a source of background hiss that was 100 times stronger than they expected. It was detected day and night and was evenly spread across the sky, so it was not coming from a single point source on Earth or in space. It was clearly from outside our own galaxy, and they could not explain it. Luckily, just 37 miles away in Princeton, New Jersey, physicists Robert Dicke, Jim Peebles, and David Wilkinson were working on a related problem. In the 1940s, George Gamow and Ralph Alpher had predicted the existence of background noise left over from the Big Bang, when everything exploded with a big blast of radiation. The Princeton scientists were just beginning their experiments to detect this noise when a friend told Penzias that he'd seen a preprint of a paper by the Princeton group that predicted the exact same background noise. The two groups got in touch, and Penzias and Wilson showed them what they had found. Lo and behold, the two Bell Lab scientists had accidentally discovered proof that the Big Bang had actually happened. For this discovery, Penzias and Wilson eventually received the 1978 Nobel Prize for Physics, and this discovery had been made entirely by accident. These stories are classic examples of how pure scientific research leads to amazing discoveries. Sometimes discoveries are made by people looking for an answer to a specific problem. But more often than not, scientists and engineers make important breakthroughs doing pure research for its own sake. Most of the best science is done by gathering a broad range of data on a particular topic without knowing what we might find. Politicians and many other people often scoff at research that does not have a definite goal in mind and try to withhold funding from these projects. But pure research is how nearly all the greatest discoveries of science are made, and science would come to an end without it. And so would all the scientific breakthroughs and life-saving discoveries that benefit us all. Since this discovery, the Big Bang model has undergone many modifications as physicists use the properties of matter and the equations of physics to figure out how it all happened. The most recent methods date the Big Bang at about 13.8 billion years ago. At the very beginning, the universe was in a singularity, an infinitely small, high-energy region with an infinite density. 10 milliseconds after singularity, the universe was filled with high-energy particles at temperatures over 1 trillion Kelvin that were expanding rapidly in all directions. It was so hot that only radiation, without matter, existed. Space and time did not yet have the meaning we give them today, but they were infinitely warped around this extremely dense region. Over the next few seconds, the universe cooled enough to form subatomic particles, and matter, in the form of atoms, appeared in about 380,000 years. Expansion continued over the next 12 billion years, and random clumps of matter began to coalesce to form stars and galaxies and quasars. Some of these stars have already burned out and exploded, producing the heavier elements such as oxygen, silicon, carbon, iron, and so on that make up most of the matter in the solar system. In that sense, we are all stardust. Astronomy has taught us that the universe is enormous and immense beyond our comprehension, and that humans are just a tiny part of it. Our cosmic arrogance, inherited from thousands of years of culture and mythology, has been dealt the death blow. The idea that we are at the center of the universe and that the universe was created for us has crumbled under the relentless effort to discover what the universe is really like, not what we would like it to be. As Carl Sagan put it in Cosmos, "For as long as there have been humans, we have searched for our place in the cosmos. Where are we? Who are we? We find that we live on an insignificant planet of a humdrum star, lost in a galaxy tucked away in some forgotten corner of a universe in which there are far more galaxies than people. This perspective is a courageous continuation of our penchant for constructing and testing mental models of the skies. The sun as a red-hot stone, the stars as a celestial flame, the galaxy as the backbone of night. Chapter 2. The Immense Age of the Earth, the Abyss of Time. The result, therefore, of our present enquiry is that we find no vestige of a beginning, no prospect of an end. James Hutton, Theory of the Earth, 1788. The mind seemed to grow giddy by looking so far into the abyss of time. John Playfair, 1905. The concept of geologic time makes you schizophrenic. The two timescales, the one human and emotional, the other geologic, are so disparate. But a sense of geologic time is the important thing to get across to the non-geologist. The slow rate of geologic processes, centimeters per year, with huge effects if continued for enough years. 1,000,000 years is a small number on the geologic timescale, while human experience is truly fleeting. All human experience from its beginning, not just one lifetime. Only occasionally do the two timescales coincide. Eldridge Moore's in John McPhee's Assembling California, 1993. Since the beginning of recorded history, people have had different notions of when things happened in the distant past. In India and some parts of southern and eastern Asia, many cultures thought of time as being eternal and cyclic. The earth and life have no beginning or end, they are part of an unending cycle. Other cultures had creation myths, explaining how the universe began at some unique point of time in the past. In some Japanese creation myths, a jumbled mass of elements appeared in the shape of an egg, and later in the story, Izanami gave birth to the gods. In Greek myths, in the beginning, the bird Nyx laid an egg that hatched into Eros, the god of love, and the shell pieces became Gaia and Uranus. In Iroquois legend, Sky Woman fell from a floating island in the sky because she was pregnant and her husband pushed her out. After she landed, she gave birth to the physical world. The Australian Aborigines believed in a sun mother who created all the animals, plants, and bodies of water at the suggestion of the father of all spirits. Once the idea of an original beginning or creation event that founded the universe became part of Western culture, the next question asked was, how long ago did it occur? Most cultures could not imagine that the universe was more than a few thousand years old. They viewed the entire universe with Earth at the center and the stars fixed to a great celestial dome. See Figure 1.1. They thought the planets that wandered across the sky, planetos means wanderers in Greek, and the sun and the moon were carried on great wheels around Earth, as they appeared to move against the background of the fixed stars. They thought that Earth itself was created exactly as we see it today. It was perfect and had not changed since it was formed. Any evidence of change, eroding or crumbling away, was explained as being the result of Adam's sin. Until the early 1600s, nearly all people in the Western world thought of the Earth as the center of the universe. Only a few thousand years old, and unchanged since its formation, except for the decay due to the fall of Adam. The thinking of prominent natural historian John Woodward was typical of his time. In 1695 he wrote, "The terraqueous globe is, to this day, nearly in the same condition that the universal deluge left it, being also like to continue so till the time of its final ruin and dissolution, preserved to the same end for which 'twas first formed." A few decades earlier, in 1654, Archbishop James Ussher, the Anglican Archbishop of Armagh, Ireland, which was mostly Catholic then, with few Anglicans, used the ages of the patriarchs in the Bible to calculate that creation happened on October 23, 4004 BCE. Another scholar, John Lightfoot,
Sample complete. Ready to continue?